Okay, so next up we're going to be solving this second type of substitution that we hadn't done yet, the Bernoulli's equation type. But it's also going to be our application problem for the week. So it's going to be a little while until we are looking at it in that form. So just bear with me. I wrote the problem right here, though. The idea is that we're going to let age be the number of healthy children inside a boarding school made up of 1,000 children. And we're thinking about the spread of the flu over time t. And it's given by this differential equation, dH dt, the change in healthy children over time, is equal to minus h times 1,000 minus h times a, this thing right here, where a is how fast the infection spreads, and then h is how many healthy students there are, and 1,000 minus h is how many sick students there are. So what we're saying is, if you have more healthy people or more infected people, you're going to have more chances for them to encounter each other, so there's going to be more infection occurring. And then minus b times h, which is the rate at which children are vaccinated against the flu. So children stop being healthy because healthy and susceptible, I guess. They stop being that way if they become infected or become vaccinated. And this is kind of a cool example because if you took like an epidemiological modeling class, this is the same way you would formulate your like very first model, but just it's slightly simplified so that we can solve it in this class, but still cool. But what matters for us right now is being able to solve it. And so I'm going to go ahead and multiply everything through. I'm looking at minus h times 1,000 times a plus h squared times a minus b times h, or h times minus 1,000 times a plus minus b plus a times h squared is our differential equation. Or dH dt plus 1,000 times a plus b times h is equal to a times h squared. And then this looks like dy dx plus p times y plus, is equal to f times y to the n, for a being f, 1,000a plus b being p, and then most importantly, this 2 is our n value. And when we introduce the substitution, that n value for the substitution comes from the n value in your Bernoulli's equation. So now that we've kind of manipulated this differential equation the way it was written for the word problem form to look like this Bernoulli form, we know that we can use the substitution. U equal to y to the 1 minus n, so y to the 1 minus 2. Or using our variables, u is h to the minus 1, so h is 1 over u. Because h to the minus 1 is 1 over h, so when you solve for h instead, you get h is 1 over u. So we can go ahead and plug in our substitution. So dH dt plus 1,000a plus b times h is 1 over u is equal to a times 1 over u squared. And dH dt is ddt of h, so 1 over u. So that's going to be minus u to the minus 2, right? Because 1 over u is u to the minus 1. But we have to remember that u is a function of time. It's the solution to a differential equation, or related to the solution to a differential equation. And so we have to remember to write du dt by a chain rule. If you hadn't caught that it's a chain rule, hopefully you would have said, okay, I started with dHdt and didn't have a derivative left. I'm trying to replace my dHdt with dudt, so something went wrong. That could be like a quick check to tell you that things aren't going quite right. So I've got minus u to the minus 2 du dt plus 1000a plus b times 1 over u is equal to a times 1 over u squared. And then when we solve differential equations that look kind of like this, this form reminds me of solving linear equations. And when I'm solving linear equations, I don't like to have anything attached to my du dt. So I'm going to go ahead and kind of divide through by u to the minus 2, negative u to the minus 2, so that's multiplied through by negative u squared. So we're going to have du dt plus 1000a plus b times negative u squared over u is equal to a times 1 over u squared times negative u squared. Here, I'll actually write the times here too. That way you see that the reason it's canceling is because of what we're doing. So those cancel out, and I have du dt minus 1000a plus b times u is equal to, those cancel out too. I'm just left with minus a on that side. And that's a linear equation. So I can go ahead and solve it using the linear equation method that we learned in class already. And let's see, my P for this is going to be that minus 1000a plus b. So my e to the integral of p dt is going to be e to the integral of minus 1000a plus b with respect to t. So that's just times t. And so the ODE ends up being e to the minus 1000a plus b times t times du dt minus 1000a plus b times u equal to minus e to the minus 1000a plus b times t times a, or ddt of e to the minus 1000a plus b times t times u equal to minus e to the minus 1000a plus b times t times a. That's just our linear equation approach, and then we integrate both sides. To make my bracket smaller, I can do this. So let's do very narrow parentheses. Integrate both sides with respect to t. So I'm going to get e to the minus 1000a plus b times t times u equal to, even though this is messy, it's just a simple exponent. So we're going to have negative a over negative 1000 a plus b e to the minus 1000 a plus b times t plus a constant. So u is going to be a over 1000 a plus b. The e's cancel out when I multiply e to the positive 1000 a plus b times t. And my c gets that in front of it. So I was just isolating u. And then from here, I have to do my back substitution. So h is equal to 1 over u. So h is 1 over that whole thing we just found. just like that. And I don't think there's a nice way to simplify it, so I'm just going to go ahead and stop there. That tells you the number of healthy students at any given time t.